Hello, my name is Mohamed Nurfiyev, and I'm a data scientist at the Institute of Smart Systems and Artificial Intelligence. Today, we will be covering digital number representations. First of all, let's start with a formal definition of a number. Number is a mathematical object used to count, measure, and label, and we represent them by symbols called numerals. For example, 8 is a numeral that represents the number 8. Knowing that there are a lot of objects to count, measure, and label, we need a numeral system to represent any number. Our ancestors have invented and developed such systems. Nowadays, Arabic numerals are the most widespread and commonly used numeral system. But as you can see, there are a lot of them belonging to different cultures and countries. But here's the question. What is common thing among all? Well, the common thing among them is that they use 10 digits. The accepted name for these numerals is decimal system. The reason why all of these numerals use 10 digits to represent numbers might be that we have 10 fingers on our hands. When we have a little notion about numbers and numerals, let's recap the decimal system. As you already know, we have 10 digits starting from 0 to 9 to represent the numbers. We can combine these 10 digits to form and represent any number we want. Let's look at the example. Let's form the number 128. To form the number 128, we can take 1 of 100, 2 of a tens, and 8 of ones. As you can notice, the number can be written as a sum of powers of 10. Using this technique, we can represent any number we want using a decimal system. But we have one problem related to a decimal system. We cannot use it to represent the numbers in computers. And the question is why? Because computer is a digital system. And in digital systems, we use voltage levels to represent on and off states to build logic and arithmetic operations. These binary on and off states are achieved by transistors. If you ever have wondered what is a transistor, transistor is an electronic device that enables one electrical input signal to control another electrical input signal. Basically, it can be understood as a switch. Using these switches, we can build the logic gates. For example, central processing unit of computer consists of millions of these logic gates. So, having the fact that we have binary states in computers, we should move from decimal system, which is base 10, to a base 2 binary numbers. In these binary numbers, 0 and 1 correspond to off and on states of transistors. These binary digits are used as the smallest units of data in computers. As we have already mentioned, these bits are encoded by on and off states of transistors. We have told that using numeral systems, we should be able to represent any number. But how do we really represent the number using only two values? As in the case of representing numbers using decimal system, we can break the number into parts. For example, let us consider the number 7. As you can see, 7 is a composition of 4, 2, and 1. As you might already have guessed, 4, 2, and 1 are the powers of 2. So we can rewrite the 7 as a combination of 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. Like in the decimal system, we construct the 7 using combinations of powers of 2. In the end, we get the binary representation of number 7, which is 1, 1, 1. The next step is to learn how to convert decimal to binary. Converting process is fairly simple. We do it by successive division by 2 and writing out the remainders. Let's quickly convert 29 into binary. First, we divide it by 2 and write out the 1. Furthermore, we divide the result, which is 14, by 2 and write out the remainder. Next, we divide the 7 by 2 and get 3 as a result and 1 as a remainder. As a last step, we divide the 1 by 2 and get 1 as a result and 1 as a remainder. First remainder of division by 2 is called the least significant bit, and the last remainder is called the most significant bit. When constructing the binary number, we start with the most significant bit. So the number 29 will be 11101 in binary. As a check for correctness of obtained result, we can revert the binary representation to decimal by multiplying the binary digits to corresponding powers of 2, and you can see it from the last table. You might wonder, how many bits will I need to represent a number? Here's a table with a length of a bit and how many values it can represent. Quick formula would be to take 2 to the power of how many bits we have. For example, if we have 5 bits, we can represent 32 numbers. Sometimes computer engineers need to write out some long binary quantity. For example, the binary representation of number 9552267 is a long number with a bunch of zeros and ones. Even reading it is tedious and error-prone for humans. So we need a compromise between binary for computers and decimals for humans. As a solution, people came up with octal and hexadecimal number bases. Let's quickly cover this too. Octal representation is base 8. We use here 8 digits to represent the numbers. The good thing about octal representation is that it has more symbols, which is natural for humans and close to decimals. But more importantly, every digit of octal representation corresponds to 3 binary digits. The binary number we had before can be broken into groups of 3 digits and converted to octal very easily. For example, the first 3 binary digits, which are 100, is 4 in octal representation. The next representation is hexadecimal, which is base 16. It has even more symbols to represent the numbers, and every hex digit represents 4 binary digits. As in the case of octal number representation, we can divide the binary into groups of 4 digits and easily convert to hex and back. There is a high chance that you have already encountered the hex numbers when programs report errors. Usually, they show the code of error in hex digits. In this table, you can see the relation between values of different representation systems. So far, we have covered how to represent positive natural numbers using binary digits. But what about the negative numbers? We cannot put the negative sign. But why? Well, we cannot put the negative sign because everything is represented by zeros and ones in computers. Therefore, we should find other ways. Actually, there are 2 possible solutions, and they are ones complement and twos complement. Let's talk about the ones complement in more detail. Briefly, to create the ones complement, we simply toggle each bit. 0 becomes 1 and 1 becomes 0. Let's consider an example of a ones complement. We will use 5-bit register to represent the positive 5 and the negative 5. In the first table, you can see that we designated 1 bit for representing the sign of the binary. And the rest is positive 5 in binary, which is 0, 0, 1, 0, 1. To make it negative 5, we toggle each bit and get the result as in the second table, which is 1, 1, 0, 1, 0. Notice that the sign bit changed from 0 to 1. The possible range of values that can be represented using ones complement can be calculated using the formula on the video, which is from -2 to the power of n minus 1 minus 1 to 2 to the power of n minus 1 minus 1. As an example, let's calculate the range for 16 bits. We will use the before mentioned formula. We have n equals 16, which corresponds to a number of bits, and we reduce 1, since we reserve 1 bit for a sign. Putting all the values to formula, we get that range is equal to from minus 32,767 to plus 32,767. But we don't use ones complement frequently, because it has ambiguity in representation of 0. 0 can be represented as zeros or ones. Another reason is that ones complement is hard to use for binary arithmetics. So there is a second solution, which is twos complement. To form the twos complement, we invert all the bits, like in the ones complement, and add 1. For the range for the twos complement with n bits, the formula would be from -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. Note that in 2's complement we have only one representation of 0. So, as an example, let us represent the positive 5 and the negative 5. The positive 5 is represented as usual as 0, 0, 1, 0, and 1. To represent the minus 5 using 2's complement, we invert the bits as a first step and then add 1 to the obtained value as a second step. Inverting the bits, we get 1, 1, 0, 1, and 0. And then we add 1, and we get 1, 1, 0, 1, and 1. Let's check for the correctness of obtained result. We got 1, 1, 0, 1, 1 as a negative 5 represented using 2's complement. And to convert it to decimal, we multiply each digit of binary by corresponding powers of 2. In this case, we have minus 1 multiplied by 2 to the power of 4 plus 1 multiplied by 2 to the power of 3 plus 0 multiplied by 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0, which is negative 5. After covering the negative numbers, we should learn how to represent the fractions using binary digits. Firstly, let's recap that we compose numbers using the powers of 2. As you can guess, we can compose the fraction parts using the negative powers. Let's cover the whole process in more detail. Suppose we have 0.8125 in decimal and we want to convert it into binary. While we use successive division by 2 when converting from decimal to binary, we will use successive multiplication by 2 here. First, we multiply our number by 2 and write out the significand. In our case, we got 1.625 from the multiplication of 0.8125 by 2, and we write out the significand, which is 1. Furthermore, we multiply by 2 the fraction part of the result. Here, the fraction part is 0.625, and multiplying it by 2, we have 1.25, and we write out the 1. Furthermore, we multiply the 0.25 by 2 and write out the 0. And then we multiply the fraction part, which is 0.5 by 2, and got the 1. Since we don't have any fractional parts, we stop it here. When writing the binary from the significance, we first write the most significant bit. And we got 1, 1, 0, 1 as a result. But what if we had a decimal fraction with significand? For example, 5.8125. Well, in this case, we break the process into 2 parts. First, we convert the significant part as before with successive division, and then convert the fractional part with successive multiplication. Finally, we combine the results. In this case, we have 0.1101. Now it's time to talk about how the numbers are processed and stored in the computer memory. One way of storing the numbers in memory is fixing the numbers of bits. Basically, we reserve some amount of bits to represent the numbers, and it's called fixed point numbers. For example, let's allocate 5 bits for the integer part and 5 bits for the fraction part. So the largest number that we can represent would be 0.1111, and the smallest would be 1000.00000. Note that the first bit is used for representing the sign of the number. As you can see from the video, the magnitudes of the numbers are not big. It is only 15.96875 for the largest number. You might say that we encounter problems when we have to deal with the bigger numbers, but we have allocated only a small amount of bits. One solution that immediately comes to mind is that we could allocate more bits beforehand. But in reality, most hardware use 32 or 64 bits, so we have limitations in our hardware. We need another solution for this. The solution is to store and represent the numbers in floating points. Let's recall that we use scientific notation to represent large numbers in decimals. For example, the number 12,345 could be written as 1.2345 multiplied by 10 to the power of 4, where the 1.2345 is significant and 4 is the exponent. So, when using the floating point numbers, we do not allocate bits for the integer part nor the fractional part. Instead, we reserve bits for the significant and bits for the exponent. So the final form would be sign bit, exponent bits, and mantissa bits. And the number would be positive, negative, mantissa multiplied by 2 to the power of exponent. Nearly all hardware and programming languages use floating point numbers. As we have already mentioned before, we have 32 and 64 bits in hardware. Sometimes 32 bits is also called single precision. For the single precision case, we have 24 bits for the significant, and one of them is sign bit, and 8 bits for the exponential part. The smallest number that could be represented is minus 3.4 times 10 to the power of 38, and the largest number is 3.4 times 10 to the power of 38. For the double precision case, which is 64 bits, we have 53 bits for the significant part and 11 bits for the exponential part. And the smallest number that could be represented using double precision is minus 10 to the power of 308, and the largest number is 10 to the power of 308. When covering the floating point numbers, we should also learn about the machine epsilon. Machine epsilon is a maximum relative error due to the rounding of a floating point number. Basically, it is how much error could occur when representing the numbers in floating points. For the 32-bit case, the machine epsilon is 2 to the power of minus 23. And for the double precision, which is 64 bits, the machine epsilon is 2 to the power of minus 52. With it, we end our video today. Thank you for your attention.